Welcome to Spaceverse, your portal to cosmic adventures. When the James Webb Space Telescope, a $10 billion marvel of modern engineering, turned its powerful infrared gaze toward the distant exoplanet K2-18b, an intriguing discovery was made. Nestled 120 light-years away, this mysterious world revealed traces of dimethyl sulfide, a sulfur compound that, on Earth, has a very exclusive origin: living organisms. Naturally, this sparked excitement across the scientific community. Could this be it? A long-sought answer to humanity's most enduring question: are we alone in the universe? Is the presence of DMS on K2-18b the cosmic clue we've been waiting for? Not so fast. While some scientists are ready to pop the champagne and celebrate this potential breakthrough, others are urging caution. Even with its remarkable capabilities, the James Webb Space Telescope has its limitations. To jump straight to conclusions would be premature. After all, in the great cosmic detective story, evidence demands thorough examination. Now let's talk about dimethyl sulfide, or DMS for short. Unless you're a chemist or a science enthusiast, you've probably never heard of it. Yet, you've almost certainly encountered it before. Remember that distinctive salty tang you notice at the beach? That's DMS in action. This compound is produced by tiny marine algae called phytoplankton that drift in the sunlit layers of the ocean, and it's part of the chemical cocktail responsible for the iconic smell of the sea. But DMS is more than just a seaside scent. It's special because, as far as we know, its production on Earth always involves living organisms. That's why scientists consider it a biosignature, a potential sign of life, when searching for extraterrestrial habitats. Its detection on K2-18b has elevated this exoplanet from an intriguing candidate to a headline grabber in the quest to uncover alien life. So, are we on the brink of rewriting our understanding of the cosmos? Maybe. But the road to confirming extraterrestrial life is as winding as it is thrilling, and DMS is just one piece of a much larger puzzle. One thing's for sure, science has never smelled this exciting. It's no surprise that the Cambridge astronomers were bursting with excitement in September 2023. After all, they had just received a groundbreaking piece of news that would forever alter our understanding of life in the universe. The James Webb Space Telescope, the most advanced space observatory ever built, had made an extraordinary discovery: a potential biosignature on the exoplanet K2-18b. This discovery was nothing short of revolutionary, as it suggested that life might not be confined to Earth after all. The team, led by the brilliant astronomer Niku Madhusudhan, could hardly contain their exhilaration as they reviewed the data and confirmed the detection of a molecule that is strongly associated with biological processes on Earth: dimethyl sulfide. Madhusudhan described the team's reaction as one of sheer astonishment, unable to believe what they were witnessing. And who could blame them? After all, dimethyl sulfide is typically produced by microbes in the Earth's oceans, and its presence on a distant exoplanet opens up the tantalizing possibility that life in some form might exist on planets far beyond our solar system. To find such a complex molecule in the vast expanse of space is a monumental step toward answering one of humanity's most profound questions. Are we alone in the universe? The shock of this revelation quickly turned into a wave of enthusiasm, with reports hailing the James Webb Telescope as a game-changer in humanity's cosmic quest for life. But hold on, does this discovery really mean that alien life, however microscopic, is thriving on K2-18b? If DMS is only produced by living organisms here on Earth, why hasn't NASA declared that we've found our extraterrestrial neighbors? As is often the case in science, the answer lies in the fine print. The discovery of DMS on K2-18b is indeed promising, but the situation is far from straightforward. However, it's worth noting that the conditions on this exoplanet are anything but discouraging. If nothing else, this breakthrough reminds us that the journey to uncovering the secrets of the universe is as complex as it is exhilarating. Could the water world be a cradle for life? Roughly 120 light-years away in the constellation Leo lies an intriguing celestial candidate, K2-18b. This exoplanet is under exciting scrutiny for being a potential Haitian planet, a world completely covered by water and possibly capable of supporting life. Discovered in 2015 using the Kepler Space Telescope, K2-18b orbits within the habitable zone of its host star, the red dwarf K2-18. The habitable zone, often referred to as the Goldilocks zone, is the sweet spot where a planet is far enough from its star to avoid being scorched, yet close enough to maintain liquid water on its surface, a key ingredient for life as we know it. While K218 is cooler and dimmer than our Sun, K218b receives similar levels of radiation due to its proximity. It sits just 0.14 astronomical units from its parent star, completing a full orbit in a mere 33 days. Adding to the excitement are the planet's atmospheric markers, significant levels of methane and carbon dioxide, coupled with an absence of ammonia. These chemical clues strengthen the case for K218b being a Neptune-like world with an oceanic surface. If true, it could represent a groundbreaking discovery, as such exotic water worlds have so far existed only in theory. However, this oceanic paradise comes with a catch. While the detected methane and carbon dioxide are promising signs, they also complicate matters. These substances make it more challenging to interpret the data related to dimethyl sulfide, the potential biosignature raising hopes of life. Could K218b be the first water world to host life? Or will its atmospheric cocktail leave us with more questions than answers? Only time and more research will tell. Unraveling the biosignature mystery. The detection of dimethyl sulfide on the exoplanet K218b is far from straightforward and represents a significant scientific challenge. The signal attributed to DMS in the observational data wasn't particularly strong, which means it required a highly specialized and meticulous analysis of the information collected to even bring it to light. This faint signal raises questions about its reliability and highlights the difficulty of identifying complex molecules in exoplanetary atmospheres. Adding to the complexity of this discovery is the fact that the spectral signature of DMS appears at a wavelength of 3.4 micrometers, a region where it overlaps significantly with methane, a much more abundant molecule in the same dataset. This overlap creates a critical challenge for scientists attempting to isolate and confirm the presence of DMS. Differentiating between the two molecules at this specific wavelength is an intricate process, and current technologies struggle to provide the required resolution and sensitivity to make a definitive distinction. The James Webb Space Telescope's near-infrared spectrometer, one of the most advanced tools for such analyses, is particularly limited in this regard. Scientists have acknowledged that separating the DMS signature from methane in this wavelength range is beyond the current capabilities of NIRSpec. This limitation poses a question. Does this mean the James Webb Space Telescope has reached its technological limits in resolving the DMS puzzle on K218b? Or could future advancements or complementary methods shed more light on this tantalizing signal? In the meantime, the ambiguous nature of the DMS signal invites both caution and excitement. While it underscores the limitations of existing instruments, it also highlights the remarkable potential of Webb and other upcoming observatories to push the boundaries of our understanding of exoplanetary atmospheres. Thankfully, the answer is no. While the current findings rely on indirect evidence, researchers are optimistic that definitive proof is still within reach. DMS and its breakdown products also produce unique signatures in the mid-infrared range, between wavelengths of 9 and 13 micrometers. This just happens to be the sweet spot for Webb's mid-infrared instrument, which is perfectly equipped to explore this range. With MIRI on the case, the quest for clarity continues, and the possibility of uncovering the true nature of this enigmatic biosignature is as exciting as ever. When NASA first hinted at a potential detection of dimethyl sulfide on the distant exoplanet K218b, curiosity soared. Not content with preliminary findings, Cambridge scientists decided to take a deeper dive into the mystery using the unparalleled infrared capabilities of the James Webb Space Telescope. For this follow-up investigation, the team dedicated 8 full hours of observation time to search for the elusive biosignature. Just a day or two later, they received the raw data and began the painstaking process of evaluation. However, analyzing such complex information is no small feat. It's a meticulous endeavor that can stretch across months. The silver lining? The researchers have already been at it for half a year, which means we're inching closer to definitive answers. It won't be long before they unveil their latest insights into whether K218b truly harbors traces of this intriguing molecule, and, by extension, a hint of extraterrestrial life. Stay tuned for what could be one of the most exciting discoveries in the history of space exploration. When will we be able to detect DMS? The search for dimethyl sulfide on K2-18b isn't just a waiting game. While observational data from the James Webb Space Telescope is being meticulously analyzed, astronomers are also tackling the question from a theoretical angle. Using advanced models, researchers are simulating the biochemistry of K2-18b to determine when and under what conditions DMS could become detectable. A team of researchers, led by Shang-Min Tsai from the University of California, Riverside, has conducted an in-depth study to reconstruct the possible environmental conditions of K2-18b, a distant exoplanet. Their comprehensive models aim to simulate various aspects of the planet, including its potential ocean and atmospheric composition. One of the key areas of focus is the potential for life forms on the planet to produce dimethyl sulfide, a compound that on Earth is primarily associated with biological processes. The team's simulations estimate how much DEMS might be produced by hypothetical life forms residing in K2-18b's environment, taking into account factors such as temperature, atmospheric pressure, and the chemical composition of the planet's ocean. Additionally, the models assess how DMS could accumulate in the planet's atmosphere, which could, in turn, have implications for its climate and habitability. Furthermore, the study explores the breakdown of DMS in the atmosphere due to solar radiation, providing insights into the longevity of this compound and how it could impact the overall atmospheric conditions of K2-18b. This research offers valuable new perspectives on the potential for life on exoplanets and their environmental dynamics. The results are encouraging. Theoretically, hydrogen-rich ocean worlds like K2-18b could accumulate biogenic sulfur gases, including DMS, to detectable levels. However, there's a catch. This is only feasible if the planet's hypothetical organisms are extraordinarily productive. In fact, DMS production on K2-18b would need to surpass Earth's by a factor of 20 because most of it would be destroyed almost immediately by photochemical processes caused by solar radiation. There's an intriguing twist, though. If concentrations of DMS were significantly higher, something plausible on a Haitian planet, a natural protective effect could kick in. Breakdown products like dimethyl sulfide and methane thiol might form a kind of shield in the lower atmosphere, preventing further degradation and allowing the gas to persist long enough for detection. Whether this hypothetical scenario reflects reality remains to be seen. For now, both theoretical and observational approaches keep the hunt for DMS alive, pushing the boundaries of our understanding of alien worlds. A groundbreaking moment in space exploration. There's no question that confirming the presence of dimethyl sulfide on K2-18b would be nothing short of a historic achievement in the field of space exploration. As the Cambridge team continues their detailed analysis of the new data, the lead scientist has emphasized that even a single definitive detection of DMS could completely transform our understanding of life beyond Earth, catapulting science into a new era. This potential discovery holds immense significance because humanity has spent millennia pondering the age-old question: are we truly alone in the universe? For generations, the possibility of extraterrestrial life has captured our imaginations, sparking countless debates, research, and speculation. Now, the prospect of finding actual proof of life, albeit possibly microscopic, on a distant world would bring an end to centuries of speculation with a single groundbreaking revelation. It's fascinating to think that all it could take is one small molecule, one key discovery, to shift the trajectory of science and the way we view our place in the cosmos. Such a moment would forever change the way we look at planets, moons, and the vastness of space itself. The implications would go far beyond just confirming the existence of life. It would open up endless possibilities about the nature of life in the universe, how it forms, and where it might exist beyond Earth. While K2-18b may currently be the most promising candidate for such a discovery, it's important to remember that the search for extraterrestrial life is ongoing. At this moment, however, no other exoplanet has captured the same level of attention or offers such a promising lead in our quest to find life in space. It's exciting to think about how the findings on K2-18b could lead to new breakthroughs and push the boundaries of what we know about distant worlds. As we eagerly await the next stages of research and the development of more advanced technologies, one thing remains certain: the discovery of extraterrestrial life, whether on K2-18b or another distant exoplanet, would be a momentous milestone in human history. Such a breakthrough would redefine our understanding of biology, challenge our assumptions about the uniqueness of Earth, and profoundly reshape our perspective on humanity's place in the cosmos. The implications of detecting life beyond Earth extend far beyond the scientific realm. It would inspire philosophical, cultural, and even theological reflections on our existence and the interconnectedness of life throughout the universe. From a purely scientific standpoint, identifying even the faintest evidence of alien biology would open up an entirely new field of study, providing clues about the diversity of life forms, their potential adaptations to exotic environments, and the conditions necessary for life to thrive. And that's it. Thanks for exploring the cosmos with us here at Spaceverse. If you enjoyed diving into the mysteries of K218b and the hunt for extraterrestrial life, be sure to like, subscribe, and stay tuned for more exciting discoveries. We're just getting started. See you in the next video.